second round of Chemenigma 2021 finals, the subjective round. We are joined by our judges, Dr. Shantanu Mukherjee, Associate Professor at IISc, Dr. Devashish Dash, Assistant Professor at IISc, Dr. Garima Jindal, Assistant Professor at IISc, and Dr. Nagafani, Assistant Professor at IISc. We will now start the subjective round, in which the participants were given 3 questions, out of which they could choose to solve any number of questions and present the solutions to the judges. Please note that in this round, the overall aesthetic and the presentation itself will not be given as much value as a solution. And so we have allowed, other than typical PowerPoint presentations, handwritten solutions, PDFs, Word documents, etc. to be presented. We shall start with Team F this round. Team F, please go on and you can share your screen and present your solution to the judges. And please remember to properly state the nature of the problem to the judges as well as you state the solution. Shomodipta Vishesh and Shagota Shaha.
Yes, can you hear me?
Yes, we can.
So one of the problem will be presented by me and another problem will be presented by my partner, Sagoto.
Please note that the time of the duration of the presentation should not exceed 12 minutes, following which you will be asked questions for a duration of 8 minutes. So however you want to present, please make sure that the total duration is within 12 minutes. You will get a notification at 6 and then at 12. Actually, we'll do you one better and give you at 6, 10 and 12.
Fine.
Okay, you can start anytime you're ready and share your screen.
We'll start counting the time from the time you share screen.
Just to confirm, this is Team A, correct?
Yes,
So
going
this
the
is
other way around.
Team F.
This is Team F.
F.
Okay.
So this round we are going from F to A.
Okay, all right, okay.
Yes, your screen is visible now. So are you guys ready? Shomodipta? You're
Yes,
muted.
on mute.
So is my presentation visible and I'm audible too?
Yes, now you're audible and your presentation is visible to us. So you're ready?
Yes.
Okay, so your time starts now.
So I'm going to present about iron 4 complexes and about the questions in it. Briefly, as the question was explained, we can see a complex where there's iron 4 and it can be easily stabilized by the tyrosine in it as an example of catalase. So the first question says, as iron 4 is D4 system, so in case of strong ligands, it would the electrons here would pair up and it would form T2G4 and EG0. And in case of weak ligands, there would be high spin state and it would form T2G3 and EG1, and in case of moderately strong ligands, it would again form T2G4 and EG0, but here all the electrons might not always pair up. So there we can see 2 electrons are pairing up and other remains as unpaired. And in the second case, second question, it shows if the strength of the end donor atoms are increased, then the Q band intensity would increase. That is from transition from the S0 to S1, and then the Sode band intensity, that is from S0 to S2, it would go blue shifted, that is a higher energy shift, and the peak would gradually increase. This is the observation when what we can see from if the strength of end donor atom is increased. Now if the strength of the axial ligand is increased, then the charge transfer band's intensity increase. We can see there is ligand to metal charge transfer. So if we increase the strength of the axial ligand, then the ligand to metal charge transfer process intensity would. That's the observation we can see from the complex. Sadly, I cannot draw the graph because of the time issues. I had to so I could not do it all very correctly. Now for the second, we have to calculate the energy. Now to calculate the energy, first light was shown on RuBp3Y2 complex, and then it was forming a unstable complex which has electron volts, which has stopping 0.04 electron volt. So the total energy required can be written in such a way that H nu required would be work function plus the Gibbs free energy from the transformation +2 to +3 as this complex is again changing to +3. So the energy required for this purpose. So here we can calculate the work function to be 0.04 electron volt plus the delta G, and the delta G we can calculate as the reduction potential and the oxidation potential of the two complexes are given, and hence we get a delta G of as it is a 1 electron process, so 1 into 0.86 minus of 1.26 the value is, so it is minus 2.2 volt. So we can calculate the energy to be, this is a Faraday constant, so 1 into 2.2 into the Faraday constant, and this would give us the energy. I couldn't calculate it actually because of the time issues. I again regret it. Now for the second part, the second questions, in the effect of axial ligands, as the electronegativity of the axial ligand increases, we can see there could be an increase in the oxidizing power, as it can stabilize the complex kind of. The electronegativity, it forms a charged species, so it can easily stabilize the complex. Now in the third question, the homos part, there are two homos specifically in the porphyrin complex. There are A1U and A2U. They are termed as B2 and B1, as we can see from the Gauterman 4 orbital model. Now A1U, either A1U or A2U is singly occupied, but here B2, that is A1U, is higher in energy than A2U. So the actual homo is A1U. So we can see here. So if there is if there are two electrons, it can easily go into the B1. Now to present the solutions, of the reaction part. Now if the reaction in the question 4, if the reaction were to be ionic, then the HOMO would be higher in energy for receiving electrons. As the HOMO is higher in energy, that would kind of catalyze the reaction than the radicals. As the electrophilicity is increased, so as increase in electrophilicity increases the energy of the HOMO, so it would kind of better the reactions. Now for predicting the product of these reactions, we can predict in such a way that radicals are less reactive than charged species. Hence, the charge form on this can stabilize the intermediate. So the charge will form on such kind of
6 minutes.
On a molecule that can kind of stabilize it. So like here we can see if in case of radical species, the 1 degree radical is stable. So in case of radical 1, the product form would be the oxidation of this CH3 and it would form CH2OH. And in case of ionic 1, the benzene phenyl ring can be easily oxidized and it can be made to phenol. That's what I had for part of me. Now my friend Sagoto will take part of this fuel crisis.
You can go ahead.
Yes. So shall I share my own screen, or will I do it here only?
It's fine if you do it here, no problem. It's just the time, you're wasting time. Come on, fast.
Okay. Okay. Yes. 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 So this is about the fuel crisis. There was a general description of the tests given, and the elements, the species that is, which would respond positively to it or respond negatively to it, or show indeterminate response. So in this picture, the cross indicates negative response. The cross with an I in brackets will indicate indeterminate response, and the tick will indicate positive response. Now, as the question suggested, that the only way to properly identify the species would be through a positive reaction, and indeterminate reactions, of course, are unreliable. So, in order, I have carried out tests 1, 3, 4, 5, 6, 7, and 8, and at the end of which we can distinguish all 10 elements as is available from the data. So, for instance, A and B are indistinguishable after tests 1 and 3, but after the fourth test, there is test 4, A and B can be distinguished since B responds to it positively while A responds negatively. So similarly, at the end of all the tests, the 10 elements can be distinguished uniquely. That's all I have to say. Thank you.
So that's the solution from your part, right, Shomadipta and Shagutta?
Yes.
Okay, so can you please unshare the screen and then we can start with the questions from the judges.
I think
Oh, let the screen be there. Let the screen be there.
Okay, let the screen be there. Okay.
because they need to refer to something.
Yeah, so can you please share it once more? Your presentation. Yeah. Thank you.
Yeah, can I ask a question?
Yes, sir. So now the judges can ask.
Yeah, can you go to the first page or the first slide? Yeah, no, yeah, this one. So you said the strong ligand will have the electrons paired in the T2G, and the weak ligands will have all of them unpaired. So what's the reason for that? Hello, Somadipta?
He has to unmute. He has to unmute. Yeah.
Your microphone is muted. Yeah, now it is fine.
So actually, in case of strong ligands, the ligand would increase the del zero value. So 10dq value would be increased in case of the strong ligand. So here the electrons.
Why does it happen? Why do they increase the 10dq or the del zero? What do you understand by strong ligand?
So by strong ligand, we mean that the splitting between the T2G and the EG is very high.
Yeah,
the electrons
that's
will
what.
prefer pairing up.
That will be reflected in the 10dq or delta zero. But do you know why the value of 10dq increases?
So actually, it could be understood from the repulsion between the electrons and the ligands. So in case of the strong ligands and the electrons of the d orbital, so there is a high repulsion between, so the split is very high. So but in case of weak ligands, the repulsion is not that prominent to make such splitting.
Okay, fine. And you said in the case of moderately strong ligands, there will be partial pairing, right?
Yeah.
Can you explain that?
Sir, here it can be said that the splitting is not the mean pairing energy. The mean pairing energy is more comparable to the 10 DQ value. So it is neither that there could be only pairing of electrons, or it can be said that there like it can be the 10, as the 10 DQ is more or less comparable to the mean pairing energy. So it can either happen that all the pairs might not be paired up, or it might pair up. So it depends on the mean pairing energy and the 10 DQ value.
No, but if the 10 DQ and the pairing values are comparable, then one of the electrons should have gone to the EG state, right?
Yes.
So, because what pairing energy has to do with the pairing or unpairing in the TTG step, in the TTG level.
So there is a possibility that it can happen. There is a possibility that it can happen, but it can. But the possibility of having like all the two electrons paired up and two unpaired electrons cannot be ruled out in that sense.
Okay. Okay, I am done. I think anybody else wants to ask.
Can I go? I just have two short questions.
Yes, ma'am.
Yes.
Yeah. Okay. So Somatipto, like, in that question, you're giving the cytochrome P450s, right? So do you know what is that 450 number? What does that mean?
Yeah, that 450 means that it absorbs the maximum at 450 nanometer. So we give the number as cytochrome P450.
Okay. And in that compound one, like, the iron 4 complex that you're showing, right? It's a radical cation, right? So where is the radical centered?
The radical.
Yeah.
The radical center is at the porphyrin.
And can you think of any neutral, isomer for that one? Like here it is iron 4, right? And you have a radical cation. Can you think of anything else, any other structure with a different oxidation state?
Yeah, like Mn3 plus in case of SODs.
No, I'm just asking for iron.
Like, ma'am, I did not get your question. Can you please clarify?
You have an iron 4 radical cation, right?
Yeah.
Can you think of any other isomer for this?
Isomer in the sense?
Like, okay, let's say iron is in 4 oxidation state. Can you think of iron? Can it be in another oxidation state, a neutral compound over here, instead of a radical cation? Okay. Thanks.
Okay, I have a few questions. Shomadipto, can you hear me?
Yes, sir.
Yeah, at your beginning sentence, you said that iron 4 can be easily stabilized. Do you think that's the right way to talk about it, or that's a correct thing to say?
No, it is not as stable as the other two oxidation states. I meant that iron 4 can be stabilized in oxo species.
So can you tell me how we can stabilize it?
So in case of
yeah.
So in case of, if we have ligands that can like iron 4 is a very unstable and high oxidation state species. So in case of iron 4, we need some ligands that can back donate electrons to iron 4. So like in case of oxygen can back donate the electrons to iron 4. So in that case, it can stabilize iron 4 in such a way. Or if we think of a model where the ligands would donate electrons to iron 4, that can in a way stabilize rather than like having some electron.
So this enzyme that you're talking about, cytochrome P450, it goes through iron 4 state, right? And it doesn't have any other ligands. The ligands are fixed. So how it will be stabilized? Did you understand my? Yeah.
So, sir, here in catalase, we can see an example. That unusual oxidation state is usually the ligands in case of heme are this imidazole groups of this, but in case of catalase we can see a tyrosine, and the tyrosine molecule can like donate an electron, or like, and it can help in conjugation in such a way.
Conjugation? No. I mean, see, catalase or cytochrome P450, they have similar active site, right? Iron porphyrin, right?
Yes.
And cytochrome P450 goes through compound 1. So you said that it can be stabilized. That's why I'm coming back to the question: how it can be stabilized? Can you tell me experimentally? It can be stabilized. Can you think of anything? Can it be seen by any method?
So actually, it can be traced by like the stretching frequency between the iron and oxygen. It has a specific iron oxygen stretching frequency of iron 4 and oxygen. So we can trace it by IR.
Can see something by IR, you have to have a very stable compound, right? And I'll tell you that this is very, very unstable. That's why it's a very reactive species. Okay. Anyway, so I have another question. If you go to the next slide, I think where you talked about the radical and carbocation. Next one probably. Yeah, here. So you said radicals are less reactive than charged species. Is that correct?
I meant in a way that charged species are more in a way like electron hungry, or like electron rich, so it can like donate or accept electrons more readily than radicals. That's what I meant by this.
But then in nature, we see a lot of charged species. We very rarely see radicals. Why is it so?
Like in that way, the reaction may go in a very fast way. Like,
for which one?
By the charged species.
By the charge. So you're saying that cations and anions will undergo reaction much faster than the radicals?
Kind of. Yes.
Okay, I think I'm done.
Yeah, I have just a very short question.
Okay, Shanti.
Yeah. So you said that from the cyclopropane derivative, with the radical, you will get this CH3 will be oxidized to CH2OH. And
yes.
Can you explain why is that?
So I believe in the CH3, here the CH activation is easily possible, as like it is forming a 1 degree carbocation here, so it can is 1 degree radical here. Radical. So it can easily form, it can easily insert a oxygen in between, whereas in case of phenyl and the OCH3, here O is an electron withdrawing group, so it would destabilize the formation of such activation. So here I believe that CH2OH would be formed.
Okay, all right.
Just a quick question, Soumitra. Here you have mentioned that if the HOMO would be high in energy for receiving electrons. Is that what you've written?
Yes.
What's HOMO is the highest occupied molecular orbital, right?
Yes.
How is it receiving electrons? If it's already occupied?
Yes. That's a wrong one. What I meant is that if HOMO was higher in energy, it can easily like electron to LUMO. So it would kind of, if there is a high difference between the HOMO-LUMO gap, so the reaction would not go so fast. If the HOMO-LUMO gap is decreased, like if the HOMO energy is increased or the LUMO energy gap is decreased, then it would kind of catalyze the reaction. So that's what I meant. If the reaction are ionic, then the HOMO would be higher in energy for the electron donation. So I meant electron donation. I wrongly have written is receiving electrons.
Okay, I'm done. Thanks.
Aryaman, do you want to ask any quick question regarding the last question, or Professor Funny, do you want to ask any question with respect to the last question they have presented? We can do it really quick since we are already 3 minutes over time.
Yeah. So the only thing is, do you have a summary score based on?
Yes. Aryaman has is calculating a raw score apart from
Yes,
the
but
whatever.
these guys would have also calculated that, right?
Yeah, so their average cost is 52 per element. So yeah, so 60 minus 52 is going to be 8. The raw score is 8.
Okay, all right. So that's what I was looking for, that number. Okay, all right. That's fine. And one quick question actually I have regarding the first one. When you go to the B, right? I think 1B, is the field still symmetric when you have iron 4 and then the axial being strong field ligands? A question for the participants.
So could you say the question again?
1B. Yeah, so if I understand the question right, so 1B says that you want a crystal field diagram with iron 4 in an equatorial oxygen, and then the axial are strong field ligands. Is that correct? Did I get the question right?
Yes.
Yeah, so it says B is a heme complex, so iron 4 oxygen complex with a moderately strong axial ligand. So the question for you is that still an octahedrally, is that a symmetric octahedral field in 1B? Yes or no?
Actually, it would not be. Like if the electron were in the EG set, then there would be a Untitled distortion and it would be tetragonally distorted. And had the electrons been in the only the T2G set, so it would not be. It would be in, not in exact octahedral shape, but it would still be in a distorted way.
Okay. So all right. So you might, if that is what you conclude, then do you think you will change your crystal field diagram that I'm seeing on the top of this page, or do you think that's fine?
Yes, it might be a possibility that the electron in the all the electrons might not be in the T2G set. It can also be in the like in case of weak field ligands. The one electron might be also promoted to EG1, so there can be a Untitled distortion or in a distorted octahedral shape.
Okay, thanks. That's it.
Okay, we are 5 minutes past 20 minutes the planned time, so we shall. Let's move on to the next team. I hope that the judges have been able to ask all the questions they wanted, and we'll move on to the next team, Team E. That is Shayantan Khan and Shubhajit Chakraborty. Please present your answer, and please state clearly the problem that you are about to present the solution to.
Yeah, sure. So we will be presenting the solution in just a second.
Okay. Please try to hurry a bit because we are running a little late.
Yeah, so is the presentation visible?
Yes, you can start.
Just a second.
Presenting.
Can I just confirm that is it full screen or what?
Yes, it is full screen.
Okay. So we are just starting with the first question. So the first question was given about that baby warmer problem. So we are just asked to design some organic phase change materials. So, in order to maintain a constant temperature that was, given that 36.5 plus minus 0.5 degrees Celsius for 3 hours, we actually need some, non-paraffin materials because the paraffin materials were not suitable as per stated in the question. So we just looked for some organic materials which are, non-paraffinic. So they can change their state several times without, any degradation. So they are basically bio-based. So what we did basically that, they generally undergo a small volume change during the phase transitions. So we take that, some organic phase change materials from the natural sources. So they are generally, we can take as palm oil, palm kernel oil, some rapeseed oil, coconut oil, and soybean oil. So they are also non-toxic and biodegradable. So we can say that these non-paraffin models, like some polyols such as glycerol, esters such as butyl stearate, isopropyl stearate, erythritol palmitate, and also ketones like camphanilone or caprilone. So I think they are all recyclable and thermally stable. So that fulfills the model we just want. So this is basically the solution to the problem 1, baby warmer. And for explaining the next question.
Yeah, okay. So am I visible? The slide is visible, right? And I am audible also?
Yes, please go ahead.
Okay. In the first question, it was given to be determine the crystal field splitting in case of the strong and weak field ligands in octahedral symmetrical environment. So this could be in case of the weak field ligands, we could have a slow spin or the triplet state where the T2G would have all the electrons, maybe all these may be paired or unpaired also, but the EG will not have. But in case of if we consider a strong field ligand, so there would be the transfer of one electron from the T2G level to the EG level, which would eventually result in the formation of a high spin or a quintet state. For the next part, for the heme complex, in case of the iron oxygen heme complex for moderately strong ligand field, so we can have both a low spin and a high spin, depends on the nature of the ligand, and also the electrons get distributed in this manner among the d orbitals, basically the dxy, dy, or dzx, like in this manner. And in case of the high spin, one of the electron gets excited to the dz square level, forming the high spin or the high spin complex. This may be the electron distribution for the heme complex with moderately strong axial ligand. And for the second question. The second question, it was asked that what would happen to the absorption wavelength of the complex if we increase the strength of the nitrogen donor. Like if we talk of the increasing strength of the nitrogen donor atoms, then we would eventually have an increased electron density on the nitrogen atom, and thus it becomes quite pretty well efficient in donating the electrons to the acidic. We can consider to be the iron center to be an acidic center, so it will donate the electrons basically to the iron center, and which would basically weaken the iron oxygen double bond. So the double bond character will be less, and hence the FeO bond will be a little bit weak, and the IR stretching frequency of the resultant FeO bond eventually decreases, which may result in the breakdown of the pi bond and the release of the free electrons, which may go to the oxygen atom also, and which can then result in the increment. Since the IR stretching frequency is decreasing, so the increment in wavelength of absorption can be observed. Now, in case of part 2, where we are talking about the axial ligand, so the presence of axial ligand actually has numerous geometrical influences on the complex, and from some resources it was known that from some IR spectroscopy analysis was done with various strong field ligands like CN-, OH-, MECN, etc. were done to examine. Then with the help of this, the vulnerability of the FeO double bond was that is our complex of interest. It was judged, And it was found out that for the MECN ligand, from the spectroscopic analysis, it was found out that for the MECN ligand, the FeO unit becomes quite stabilized towards different substitution reactions by the ligands, by other ligands in the periphery, which hence results in the stabilization for the FeO double bond. And hence we can again give this argument that the bond will not be so easily broken and will not be giving out the free electrons. And hence it becomes a little bit difficult, which results in the fall of the absorption of wavelength. So we can say that in case of the axial ligands, due to some geometric influences that was found out during the spectroscopy analysis, the FeO unit becomes a little bit stable, and hence the bond doesn't tend to break so easily, and hence results in the fall of the absorption of wavelength. So this was all about from the question 2.
Yeah, so basically we are done with our set of solutions. So yeah, this was it.
Okay, let us move on to the questions. Professor Funny, would you like to go first with the first?
Yeah, sure. So if I remember again the question, right? So yeah, well, let me ask you a straightforward question. You said 36.5 plus or minus 0.5 degrees centigrade, right?
Yeah.
That's the most important criteria, correct?
Right.
With the materials that you chose, how are you ensuring that that is where we are? Especially the narrow range of temperature over which this phase transition has to occur, right?
Yeah, exactly. So we first of all we have to make sure that the melting temperature of the materials must be within that range. So generally the melting temperature of these materials are around like 35 degrees Celsius to within 35 to 40 degrees Celsius. So I think during the phase change occurring, they can easily maintain the required temperature to be at 36.5 plus minus 0.5 throughout the time.
Okay, but do you know if a single component material will freeze over such a narrow range? Yeah, that's important, correct?
Yeah, absolutely. Like, they can.
So did you check if any of these materials have a narrow temperature range over which they solidify or melt?
Yeah, I think the models we have taken, they shall fulfill the given narrow range temperature conditions.
Okay, is there like a plot or something that you can show to confirm your I would say hypothesis?
Not exactly. We don't have such a plot, but we just took these references from some information that is not correctly a plot, but they are generally a source where these materials can be written. At this temperature, we just check that melting point temperature, and that was they just fulfills that narrow temperature condition. So we just plotted it over here.
Okay, so one other thing is that they have to maintain a temperature of 3 hours, right?
Right.
So did you? How are you going to ensure that that's taken care of?
I think that these materials are quite stable. So I think if these are thermally stable, so we can think like they itself can maintain the required temperature to be at the given condition. So I think because they are thermally stable and they possess enough latent heat, so they can maintain the temperature throughout this condition, this 3 hours time.
Okay, are you confusing thermal stability with phase transition temperature, or because remember, I think it has to be within that narrow range of 1 degree centigrade for 3 hours. So a question is, how do you foresee this design of yours will meet those metrics?
Yeah, I think the exact reason is not known to us. Like we can just it is only said that they are thermally stable. Yeah, so I may be confusing between the thermally stable and that the phase changing temperature. So
okay.
Yeah.
Okay, and one last question: are you proposing like a single component solution, or are you proposing to make mixtures of these oils that you proposed?
No. We are definitely proposing a single component solution. I mean, each of the models that we take, like, I mean, for a single component glycerol, for a single component like some esters and like that.
Okay, all right. So I'm done with questions on this. So maybe others can ask questions on the complex or here as well. If I think I have one more
Can I
question.
ask?
Maybe I'll come back later if we have time.
Can I ask one question on this topic?
Yeah, go ahead. Yeah.
So you mentioned about using different oils. So, and you know that naturally they're pretty much okay at room temperature. But do you know the components of this oil and why there's a narrow range of temperatures there?
Yeah, so I mean the oils we have taken, like, I mean, in palm oil, palm kernel oil. So there are generally oils, like, I mean, there is stearic acid, there is palmitic acid, and like that. So we can
Just
say that
acids. Wait, just acids.
Right. Okay. So a bit sorry. Like these are not acids; these are esters. So, like, I mean,
Okay.
palmitate
What kind of
esters.
esters?
Can you please repeat your question?
Yeah. What kind of esters?
What kind of ester? I mean, they are palmitate esters. Like, I mean, there are stearat esters and like those.
Yeah, but what is the other group?
Okay.
Palmitate or stearate. What is the other group?
Right. Yeah, that is not exactly known to me. Like, I mean, right now.
Okay, and do you know, just a bit more question. Why some oils are liquid at room temperature, why some other oils are solid at room temperature?
Yeah, I think because there are many factors according on this. Like, I mean, in cases where there is hydrogen bonding, some cases where the molecular weight is very high, so we can find that
hydrogen bonding. Are you sure there is a hydrogen bonding?
Yeah, I think it just depends on structures, because I mean, some oils can have hydrogen bonding. According to my intuition, I may be wrong. Like,
so what is stearate or what is palmitate? Do you know the formula or the length of the carbon chain?
Yeah, so I mean, stearate contains, I mean, 17 carbons in it. Like, palmitate contains, I mean, 15 carbons in it, like that. They are long chain esters. I mean, not esters. They are groups. Yeah.
Okay. Okay. Yeah, I think I'm okay with this part.
The next part, I think, can you just move on to the next slide?
Yeah, sure. Yeah, or a bit later.
Yeah, no, I'm just trying to. Yeah, go to the next one.
Okay.
Or the one. Yeah, I think this is also explained. It's all right. Did you answer the cyclopropane question?
Not actually. No.
Yeah.
No, I have a question on this slide. So you have drawn this, this energy levels, while quite, similarly spread from each other. Are they like this?
Sir, we took actually, we referred to one of the citations that we have mentioned in our slides. So from these references, we got to know that depending on the nature of the ln that is taken for the nature of the moderately axial ligand, it was found to be like this arranged, in this manner, to be arranged in this manner, but it may change depending on the structure and also some geometrical aspects, orientations of the ligand.
No, the other question that I have is like, let's not complex it too much, for an octahedral complex, right? But you will have T2G and EG, right? The way you have drawn it, they look like, they're equally spaced from each other. Is it true? What do you think?
No, sir. I think that they should be a different of different levels. I mean, I have drawn it in the same energy levels, so the spaces between them are equal, but it should not be in such a case, I think.
Okay, because I just asked this question because in the later part, for the high spin, you specifically mentioned that the extra electron or the fourth electron will go to dz square. Why not dx square minus y square?
I mean, it was a bit experimental, I guess, because the electron will favorably go to the that state or that level where the energy to be excited is less. The energy spent
Can you experimentally see these orbitals? Is it possible?
No, but it was given on the geometrical interpretation of the orbitals, like how these are arranged.
Okay, all right. Thanks. I am done with this part. Thanks. Sorry, Santanu. I just
No problem. That was it's fine. Yeah, I'm also done. I don't have any question here.
I wanted to ask one thing over here. You said that. So can you clarify in the previous slide which diagram is for which kind of ligand?
Yeah, sure. Shantanu, please, the previous slide.
Is this, I mean, this slide?
No, the next one. The next one.
Okay.
Yes.
Yeah. For the weak field ligand, the T2G level remains completely filled, and the EG, the electron is not excited to the EG level, and we get a low spin state as a result of this in case of the weak ligand. And for the strong ligand, a splitting, the excitation of the electron takes place to the EG level, and as a result of which we get the high spin.
So are you sure that for weak field ligand you get low spin and for strong field ligand you get high spin?
It depends upon the
no, for this D4 only. For D4 only. You're sure that for weak field you get low spin and for strong field you get high spin?
Yeah.
Sir, if you don't mind, can I just interpret? Like, I'm sorry. Hello.
Yes,
yeah.
please.
So I think I mean it is wrong. Quite. I mean, for a strong field ligand it is low spin, and for weak field ligand it is high spin.
Okay.
Yeah.
Okay. Yeah. Okay. Professors, you can take it from here. I just wanted to clarify this.
No, I don't have any more question here.
Okay. Do any of the professors have any more questions? Otherwise, we can see if anyone on the floor has any questions. Okay, we have about 2 minutes left. If anyone from the floor wants to ask any questions, please unmute yourself and feel free to ask. Okay then. Seems we are done with this team then. Let us move on. Okay, Shantanu, you can unshare your screen right now.
Okay, sure. I'll move
on. Yeah, we can move on to Team D. Team D has Hardik Rajpal and Kumar Satyam. Kumar Satyam is not present from IIT Bombay. Please share your screen and you can start.
Right.
A solution.
Right. Visible as a pointer?
Yes.
Yes, it is.
Okay. So about the question, it was the one where we land on a planet and we have to come up with a strategic method for analyzing the presence of these elements in the raw materials that we find around the planet. And we were supposed to minimize an average cost per element to maximize our marks. And I wasn't really clear about that definition, but I'm fairly certain that the general strategy that I followed here is good in the best sense. I'll see that I followed, and that is, first we go through the list of general tests, not the confirmatory ones, and find a test that divides the contending elements between roughly groups of two that are nearly half. with as few elements as possible in the indeterminate slab. And then, so I ideally was looking for only one element in the indeterminate slab, like H over here, and there's F over here. And then before we go any further, we first check for the presence of that indeterminate element, like H was going to be indeterminate for T10, the test. So first I checked for H, and then I don't have to worry about it over here because every branch ends with a confirmatory test, right? Which was a part of the question, a compulsory property of our answer. So that's that. And yeah, so first we find a test that can split them into half and eliminate the indeterminate single element with its confirmatory test. And we repeat that for the splitter groups. And yeah, so I didn't have time to do that for F. I actually went backwards. I did that for H and many of the other indeterminate ones, but I didn't have time to do that for F. So yeah, first I'll use T8, then the rest is just semantics. I can explain the format that I've used, which is the test is listed here and then the contenders at every point. So first it's A to J and then I use T8. Do you all have the list of tests to know whether I'm going correct, or do you trust me, or do you want me to show the list? Anyone?
Exact solution
we have the list.
Yeah.
Okay, right. So first I use T8 and the positive, and these are the positive and negative categories. F was an indeterminate element. Like I said earlier, I was supposed to take it out, but I didn't have time to edit the hierarchy structure. So I left it there. And yeah, we come here. So then the first thing I've done is eliminate F and eliminate H in the next test. So I use T16, which is the confirmatory test for F, to eliminate it. And then I use that T18 to eliminate H. And then I'm left with these four, for which I have test T10, which can split them into halves. And then I use the confirmatory tests in the end. So like I use T20. If it's positive, then we end at J. If it's negative, we can deduce that it's C, but to avoid any confusion from indeterminate elements being present with any other tests lying from T1 to T10, we just use the confirmatory test. I see its value now, right? So that's this half of the table. And then, yeah, when we come here, again, I was supposed to remove F, I didn't. And then we use T1. So luckily in these 5 elements, T1 doesn't have any indeterminate elements. So we get a clear-cut A, B, and EFI. Then we use A's confirmatory test to get a positive A. If it's negative, it's B, but we use T12 again. And with EFI, again, we do the, here there's no point in trying to split it further because there's just 3 of them. So use the confirmatory test for I, T19, if it's positive there. And if it's negative, just use T15 to get a positive at E, and negative at, use T16 for F, right? So other than this, the understanding, other than this diagram, I do have another slide, but in the submission I only gave this, so I think I'll restrict myself here. The other is just numbers about cost calculation. So what I can say is, let me see if I can change the pointer. Right, so the way I understood it is that we were calculating the cost for every element based on the elements that we tested before it. So would give the costs for finding out if I is present. And then in addition to this, going along this road and this would give the cost for E. And in addition to these two going along, sorry, ignore this, adding the cost for T16 will give the cost for F. And I think this is a bit ineffective way of checking the efficiency of the method. The good thing, and if we calculate costs this way, the best method would be the vacuous method, where we just do 10 tests to check for the presence of each element in any raw material at all. And yeah, what I think we should have over is the root of the element individually. So well, that, and what are the odds that the element will occur in a raw material? I'm not being clear. The good thing about this method is that at almost every step, half the possibilities are crossed out. Whereas with the all 10 tests for every raw material, you have to spend 100 points for every raw material sample. So with this, if say a particular raw material has only I, right? You don't have to do the other 9 tests. You'll have to proceed through this route, and you can conclude that it only has I. we'll have to test another half of its sample for E and F. So yeah, I think that's the good thing about this method. I see I'm only halfway through, but yeah, this is the only question I had time to try, and I'm open to any questions.
Professor, if you have any question, you can go ahead and ask. And if not, we can also take questions from the floor.
Excuse me, can the participants ask questions?
We have not taken a decision on that. I think I'll leave it to the judges to decide.
Yeah, it should be fine, I think. Yeah, why not?
Okay. May I ask one?
Sure.
Okay. Just one thing. So, the context of this problem was to check whether you have certain raw elements in the material that you are using to make your fuel, right?
Yes.
So the thing is that if you, let's suppose that we are trying to check for the presence of C, if you just look at the bottom left, it's negative T13 and you have used that to confirm C, right?
No, I'm sorry. I should explain this. The test over here in the block above is, its result is listed here. So this is a negative result for T20, and then we're doing T13. Does that make sense? Like you can look at it over here. Raw material we have, and we're running, and the sample that gives us a negative test, the raw material that gives us a negative test, we'll run T16 on it. And then if its sample gives us a negative test for T16, I'm sorry, the laser pointer wasn't on. And yeah. Right. And if we get a negative result for T16 over here, that will be this slab. And then we run T18 on it. Does that help? Right.
Yes, thank you.
Okay.
Okay, we can take questions from here. Abhiram, go on.
So I like that you have tried to split it in half at each step, each test. But like if you notice, like every test also has a different cost, and some tests cost more than the others, right? So test 8 has a quite high cost of 9, and like test 5, for example, though it doesn't split it as evenly, it has a much lower cost of 5. So did you try, starting with some other tests and seeing where that goes and how the total cost comes if you try some other tests first?
Well, truth be told, no, I didn't have time to check for other possibilities. But which test did you recommend? Test 5?
Yeah, it has a split. It has a decent split and is only of cost 3. So I would think that would be a better. I'm not sure. I need to check what your total cost comes out to.
Right, and yeah. So yeah, the only one of the main criteria for me to decide the first test was should have as many determinants as possible. So I went with 8 because it seemed like a compromise between T1 and because it split it in half and it had only one indeterminate. See, T1 has no indeterminates, but it doesn't split it into half. It's like 8 and 2. So that's not very helpful.
Yeah. So I mean, yeah. So just the thing that I noticed was that the cost for test T8 is the same as the cost of T5 plus the cost of T7.
Okay.
You see that? And T5 and T7 don't have any indeterminates in common. So if you had just done those two, you would have got a much better split, right? So
right.
I wanted to ask if you noticed those kind of things, or you just went for the half-half.
No, I just went for the half-half. I didn't have time to revamp and check those things.
Right. Okay. Thank you.
So basically, you talked about the cost calculation.
Yes.
So basically, what I meant by cost calculation in this question is, suppose you have a sample, like you said, the sample turns out to be I. So you have a whole path which it follows, right?
Yes.
So the cost per element is the cost taken along the path. So for example, along this path, the cost was 20. Along for like say A, the cost was 15. So then we will average all the costs that were taken along every path. So based on this, I think you have got a very good idea of what was actually going on. Yes, because this was meant to simulate how a qualitative analysis would work in a lab, like how you would design an analysis in a lab. So based on that, I think you have got a good idea. But yeah, as Abhiram said, I believe there are possibilities of a more optimized solution.
Right.
This was more of a comment than a question. So
Right, sure.
Okay, if there are no more questions.
Right. I just want to add one more point about the cost calculation. And yeah, while I completely agree with what I couldn't see the name, I assume it was Ariman for the last comment. I do think that the compositions of these elements would play a role. I assume them to be equal, but like how common is it for them to occur in a raw material, right? And then how should I try to minimize their costs? That would have also played a role. So that's that's like a reply comment to the comment.
All right, let's then move on to the next set of solutions by Team C. Unless, of course, there are any more questions, we still have a little bit of time. Are there any more questions? Okay, then let's move on to Team C. Team C is that of Pravar Kataria and Dev Gupta. You can present your solutions and please try to give a brief understanding of the question as well.
Yeah. Is it visible?
Yes, you can start.
We have attempted to question.
It's not yet full screen in case you want to.
Yeah, it's not full screen.
Yeah.
It is full screen now.
Yeah.
Go ahead.
We have attempted two questions, the one fuel crisis and the baby warmer. The fuel crisis will be discussed together by me and my teammate, and the baby warmer will be discussed majority by me. So I will start this. Okay, so these are the tests which were mentioned. This is just as a reference. So so you do not have to open the thing. And yeah, we made a table which represents these tests and their results. So N represents the negative test result, P represents the positive test result, and O or 0 represents the indeterminate. So yeah, I will discuss briefly the strategy and the interpretation, how we interpreted the question, although it was, So it was unclear for us the first time how to proceed, but after second time we interpreted it as follows: that the traveler which is in the search of a fuel, he can segregate the component, but he is unable to identify the components. Like he has, So this is what we interpreted. Please point it if it is wrong interpretation. Like there are 10 test tubes with A to J. The labels of the test tubes are torn or not visible. So we have to identify what's in the test tubes, but we can segregate them. Is this the correct interpretation? Okay, I'll just proceed. So we have brief strategy. So we first try to distinguish two elements at a time. Earlier we tried to segregate into half and half because that looked more efficient, but segregating two elements at a time, which we will explain it further, it looks much more efficient after we tried or calculated the cost. So also there is one more kind of tactic, that if there are n-1 test tubes left, so n test tubes left, so we just test the n-1 on n-1 test tube. For example, if there are like 10 test tubes and we have the confirmatory test of A, we do it on 9 test tubes. So if it is negative in all 9, so the 10th is automatically it. And in indeterminate the indeterminate elements for the specific test, we just keep in mind the worst case. Like they always turn against us, in not in favor of our test. So always they try to interfere or increase the options as many as possible, so that our process is cost effective even in the worst case. So this is just explained in the slide. Okay, so now my teammate will take you through these steps.
Yeah, am I audible? Am I audible?
Yes, go ahead.
So we took the 10 test tubes and we added T1 to them, and T1 can give negative tests only with A or B. So we can, if the first 9 test tube only one of them give negative, we can know that the last one will always will be negative also. So we can isolate 2 test tubes from them, one of which is A and other one is B. Then we took the 2 test tubes and added T11 to them, the conformity test of A. So the one which gave positive will be A and one which gave negative will be B. Then now we have identified the A and B. To the rest of the test tube, we do a similar process and add T3 to 7 of them. And we see that only G and D will give.
Hello? I think you're not audible anymore, am I right?
Yeah, we can't hear him now. Yeah.
Yeah, same here.
Yeah, so should I continue until?
Yes, please continue, and please speed it up.
T3.
You have already spent 5 minutes.
If we add T3 to 7 of them, am I audible?
Yes, you are.
Then we can, in a similar process, we can isolate G and D and then do the conformity test of D on one of them, and the other one will be G. And we do it similar process again and again. In the remaining 6, we add 5. We add T9 to 5 of them. Then we isolate E and H. Then we identify E and H, then isolate C and I. In the last step, only 2 test tubes are remaining. So we added T10, which will give positive for F and negative for J. That's it.
Yeah, so the total cost comes out to be 192 in this case, which we considered, the worst case. Like in D and G here, in the third step, we considered that D also interferes along with G. Yeah, so we tried to simulate the worst case and calculate the cost, which comes out to be 192. Okay, so proceeding to the baby warmer question. So this is the basic introduction to phase change material. Yeah, it could release or absorb energy according to the requirement, and it is used to provide heating or cooling. It can also be used in to treat aches and all that by heating bags, and also as incubator, as mentioned in the question. There are mainly 2 types of this. The one is the phase change, which is like literally from solid to liquid or liquid to solid, which causes the change in energy. And the second is from maybe the crystalline state change, or some like not physical classical change in phase, but a change in crystalline forms or something. So that is also possible PCM material. So yeah, this is an example of sodium acetate bags. So this is in one crystalline form, and this is in other crystalline form. It occurs by applying mechanical pressure and allowing it to recrystallize. The temperature increases. This was a video, but unfortunately it couldn't play. The merger, I don't know, it just destroyed this maybe. But yeah, it was a video in which they showed that after applying mechanical stress, the temperature increased from 18 degrees to somewhat 40 degrees. Although this is unsuitable for a baby warmer, because the temperature range is pretty high, and and it is not suited to a body temperature because it's from 18 degrees to 42 degrees. Yeah, so solid PCM. So yes, the main advantage of this against the classical VCM is that this does not involve liquid state, which is difficult to handle in a PCM or a heat bag. So yeah, and it can also result in variable amounts of energy from large to just very small. Although in the case of state change, it is generally larger. Yeah, and the temperature variation is also too much, as mentioned in the last point, minus 50 to 175. So you can get any temperature you want to have as per requirement. Yeah. So in question it was mentioned as that we need organic PCM. So the advantages are that it is compatible with the conventional material of construction, which is I think the incubator. It is chemically stable as compared to salts. It is safe and non-reactive. Yeah. Yeah, and also it is water-free. So there is, whereas in the case of salt-like PCMs, they must be prevented from water by encapsulating them. So it's more cost-effective, I suppose. Yeah. So in case of solid-liquid PCM, we need the melting point to lie in the range of human body temperature because that is the temperature range which is of concern. And in the solid-solid PCM, we need the transition temperature of two crystalline forms to be in the range of normal human body temperature. Also, as mentioned in the question, we needed to find one particular PCM, but in commercial use, more than one PCMs or some extra materials are also used to stabilize the temperature for longer time and to adjust it to the to requirements. Yeah, selection criteria for PCM incubator, as mentioned, it should operate at a specific temperature range, nearly body temperature. It should be cost effective and it should maintain temperature for a long time, mentioned as 3 hours, right? So these were the possible contenders which I listed out from Wikipedia. So these were the three that were closer to the body temperature, and these were organic. So paraffin was unaccepted, as mentioned in the question. Also, camphenylone had a higher temperature range, and it also was it had higher energy of a higher enthalpy, so which causes huge temperature variations. So this is mentioned, and also in caproic acid the energy liberated is low and it has high specific heat, so making it more stable to temperature changes, which does not change the state and all. Yeah, it is mentioned that also mixture of PCMs and artificially synthesized PCMs are also used nowadays. Yeah, thank you.
Okay, we can open the floor for questions from the judges.
Maybe I'll go ahead and ask a couple questions. But first, regarding that question where you had the fuel crisis question, you're doing the same 9 times. Is that correct?
Yeah, the same test on different.
For the first.
If you go to the slide where you have written down, I think.
Yeah, this.
Yeah, essentially, I mean, you're doing the same test on 9 of them. Did you see if there is any redundancy to it, or did you think that's the most efficient way of doing it?
Yeah, we've assumed that the traveler has already segregated all the 10 elements. It's just now to find out which one is them. So I think it is essential initially to test 9 of them so that you could select by elimination that only one is left or the 2.
Okay, all right. So that's the only question I had here. And regarding the baby warmer question, although you identified the temperature, did you also look how the heat absorption or desorption is as a function of temperature? I mean, over what range of temperatures it occurs for these materials?
Yeah, no, I didn't look at that.
Yeah. Okay. So another question is: so let us say you want to do that. What kind of experimental technique would you use?
Yeah.
So now let us say you have capric acid, you decided you want to use it, and now you wanted to understand if it will give you that melting or solidification over a 1 degree centigrade range. So what kind of experiments could you carry out to arrive at the answer for that?
No, I'm unaware of the experiments.
Okay. And then the other thing is it has to withhold this temperature for about 3 hours.
Yeah.
Right. So what did you think was like a reasonable range of heats of solidification or heats of fusion of relevance for you?
Yeah, the mentioned ranges are about 150 for this, 250 for this, and 200 for this. So all in all the PCM materials that I served through, capric acid has a a comparatively less range of heat of fusion. So a specific heat capacity, so the temperature do not change much really fast. So I think that's useful.
And let me ask you another question. Now you found a material, but let us say you did a search and you found out that no single material meets your criteria.
Yeah.
Okay, and no single, I would say, single component material. So now, what approach would you take to artificially make a material that could potentially give you what you want?
One way find the flaw why it is unsuitable. For example, it is it has very less specific heat, so it just changes temperature too fast. So you could add some material or some so-called impurity with high specific heat so that it does not change the temperature. Also, you could add this PCM so that the heat is distributed over a temperature range and not at a specific point. Like if we add capric acid and camphorine in it, say half amounts. So first at 36 degrees Celsius that there will be a heat release, and then at 39, and not just at point. So it will be a more stable heat change, I suppose.
Will you, if you have two components, are you saying that the heat change will occur over a narrow temperature range? Is that what you're saying?
No, at a wider temperature range. Like there'll be, yeah.
Okay, but that's going in the wrong direction, right? We ideally want a very narrow temperature range, correct?
Yeah, we want it, yeah. Also, the concentrations could be varied, I suppose, to just more stabilize or destabilize the temperature ranges, like a more fluctuable, yeah.
Okay. I mean, let me ask you a question which is probably totally unrelated to this. What would happen to the melting temperature of water if I am chloride?
Yeah, it will low down.
Do you know why?
Because the melting point is maybe defined as when the vapor pressure of the solid state equals the liquid state. So I think it will decrease the vapor pressure of or increase the vapor pressure of this solid state and decrease the vapor pressure of liquid state. So it will take a lesser temperature to achieve that equilibrium in vapor pressures.
Okay, all right, thank you. All from me.
Hello?
Yes.
So in the first question, so like you had asked about the test tube thing is what we had meant. So no, that is not what we had meant. It's not like the 10 test tubes there. So think of it more like maybe the qualitative analysis you do in your high school chemistry, right? Where you're given a compound and you have to try to figure out which one it is. So that is the kind of thing we meant here. So if now that you know that, is there any way how we're going about it? So
yeah, definitely.
Okay, so what would be a few changes that you would make now that you know that?
Can I see?
Sure, go ahead.
So to make it more confirmatory, wherever we used, we left out one so that we said that that would definitely be the other one which we left. We would do another test on that one.
Right.
Like in the first step, we left one of the test tube for T1, so we will use T1 on that last also. When we isolated A and B, we will use T1. We will use T11 to both of them. So
Right.
in every step, we will add an extra test which we left out.
Right. Right. So yeah, it is important to confirm every element. Okay.
Yes.
Apart from that, the procedure you followed seems fine. So if it answered positive, you will do these tests. If it answers negative, you will do those tests. The procedure, the rest of it seemed fine. Of course, since you misunderstood it, the calculation is slightly off. So the cost is going to be slightly different from what you calculated. But yes, you have given a good solution nonetheless.
Yeah, I calculate the cost with this method using an extra test.
Yeah. Okay, nice solution, and yeah, that's
Okay. Are there any more questions? Otherwise, we have just 1 minute left, less than 1 minute left for questions this round. Okay. In that case, let us move on to the next team. That is Team B. Ankur Nath and Ritik Haldar.
Yes.
You can present your screen and start.
Ritik, please start.
Oh, you will present now?
Yes, I'm presenting, right? You can see my screen.
See. Audible? Anubhav, audible?
Yes.
Yes.
You can start the slideshow because.
Okay, sorry. Yes.
Has not gone to the slideshow mode.
So it's okay, I think.
Okay, if you want, you can.
I have started slideshow on my computer.
Then please escape it and just use the normal PowerPoint window.
Okay.
Yes, you can just do it because this either way does not not about the presentation itself.
Okay, I did start. Ritik, continue.
Okay, so my question is the baby warmer and how to design a baby warmer. To design a baby warmer, we did a proper combination of three properties: a proper heat exchange surface, thermal energy storage material, a phase change material. The material selected for the alloying in this baby warmer must be non-toxic and the environment friendly. The baby warmer, the thermal storage is actually a heat storage. It is the latent heat is linked to the heat release of or absorption at the time of phase change of storage material. The PCM is actually the phase change material must have its melting point in the anticipated range of temperature. Here it is 36.5 degrees centigrade. Ankur, next slide. So when a PCM freezes, it releases a large amount of energy in the form of latent heat at a relative constant temperature. Conversely, when they melts, it absorbs a large amount of heat from the environment. That's how we can make a constant temperature in the baby warmer. Now we have to check which molecule or mixture of molecules can maintain constant temperature of 36.5 degrees centigrade. For this, we can design some experiments to check these properties or check in the database to find out this type of molecules. Actually, I found a molecule of mixture of molecules which can show the 32 degrees centigrade temperature. Which is very close. We can change it is actually a mixture of two molecules which are very long change of carbon chain. So we can change their carbon chain length to get our expected temperature. How much energy they can store also depends on the material. We have to consider this. We will add a
heat sensing mechanism when it was cause the 36.5 degree temperature, and it will stop giving heat to the material, and by exchanging heat. Also, one point I missed, I think, we also need a heat exchanging surface. So by this exchanging surface, they can exchange heat to the environment, and it comes in the solid state. And our heat sensing mechanism again sense this property change, and it will detect it, and it will started giving heat. Next slide. So it is our graph for our material. You can see the when it is in the solid phase, we can start giving heat, and the energy difference between the latent heat, actually it is the latent heat energy difference between the melting state and the solid state. It is very important because we are constantly giving the heat here to, and when it melts, our heat we stops giving heat, and it comes back in the solid phase, and the cycle begins. It is my that's it for the baby warmer question. Ankon, go ahead for second question.
So the second question that we have attempted is the fuel crisis question. Now, I hope all the judges and the team members have their copies of the individual tests. So what I have done is, again,
Ankon, can you please zoom into your presentation, because
yes,
it is not visible.
Can you see it in the slideshow mode? Right.
Do not do it in the slideshow mode. There is a magnifier in your window, right? Use that.
Okay. Is it visible now?
Yes, continue.
Yes. So what my strategy was to use the minimum number of T10 plus I tests, because they have a largest cost. And also I have tried not to have any indeterminate materials that I would, indeterminate elements that I would need to check comparatively between positive result and the negative result. So I have tried to absolutely avoid that. I'm not exactly sure how effective that has been, but it seemed very unreasonable to have the elements being a part of this, because I don't exactly know how the average is being calculated. So what I have done is I have started with this which is a weight of 5, and I have divided it into 2. And for this part, I have done this mainly because B is present in a large number of indeterminate states. I think they are present in 4 of those indeterminate states in the 20 tests. So what I have done is I've tried to absolutely remove B at towards the beginning of our test, and that has been successful here. Also, there was one point which I had missed, and this is why the picture is extremely bad. Like towards the end, I realized that just a negative test won't suffice. So we need to do some sort of a confirmatory test. But for a confirmatory test, we don't need a T10 plus I test to do it. We could just use some previous test which has a confirmation at the beginning. So if I don't have anything in my raw material that I'll be using to make my fuel, then I'll get the necessary result using a T10 minus I form of a test. So that is how I have continued here. I have had to use a few T10 plus I tests here, which I think affected my efficiency. And this is just this is just the form of what the strategy was. So I think that's it for us. So please ask some questions.
Okay, the floor is open for questions. Professors or do any professors have any questions?
Okay, yeah, let me quickly ask a few questions. So guys, for the question on the baby warmer, did you? I think the question is similar to what I asked the other participants. Did you look at certain specific materials?
Yes, I searched in the literature, but I did not mention here. So I found that the hexadecan and tetradecan mixture have these properties, but it is not 36.5 actually. It is 30 actually, 30 degrees centigrade.
Okay, so then how do you think we can ever make this? Can we even make this work, or do you think
this is the hexadecan and tetradecan are the carbon long carbon chains. So I think if we add some more carbon in this hexadecan or tetradecan, we can achieve this temperature. I think so.
And what do you think will be the range of temperatures for some of these long chain hydrocarbons? Will it be a narrow temperature range or will it be a wide temperature range? And then why?
For these hydrocarbons, right?
Yeah, for long chain hydrocarbons. Will the transition temperature be very sharp or will it be broad? And why?
It depends on their structure, I think. Depends on
Yes. So instead of using maybe these alkanes, like in order to make the transitions very sharp, we could use some lipid molecules in that case, which I think in lipids such as POPE, these sort of lipids, they have very sharp transition temperatures, and especially if we don't have any impurities, then we wouldn't have any sort of hysteresis which would make the temperature transitions broad. So if it is pretty pure and biological lipid, then I think it might work instead of maybe mixture of alkanes.
So let us assume you have a pure material. Are you sure when you do a heating and a cooling cycle, you will not have any hysteresis?
In a pure material, I mean, from what I understand about hysteresis is that hysteresis occurs if we have two components at the same temperature, but with two different states. So something like 2 degrees and 25 degrees, if these are the melting temperatures, then at an intermediate temperature, we would have hysteresis. But in a single component mixture, if it's pure, I'm not exactly sure about why we would have hysteresis, especially if it's pretty uniform or like there aren't any sort of curvatures or anything which could cause maybe some local differences in attraction, van der Waals attractions, because the temperature ranges are mainly due to the potential energies, like the differences in potential energies. So if it's pretty uniform, then I wouldn't expect any sort of greater width in the temperature transition.
Okay, are you mixing width and hysteresis? So you could still have a sharp transition, but you can still have a hysteresis. Is that a fair statement to make?
Yes, but I'm just saying from what I have read in most places, which like I have read a few places, the lipids that were used, they had like the hysteresis and this larger phase transitions, phase transition ranges were correlated. So positively correlated. So in that case, I just assumed that they would be correlated because I've seen a few examples.
Okay, all right. So I'll come back to the first question that I started, and that also will be my last question. Do you see why in lipids you might have a sharper transition and why in alkanes you might have a broader transition? They're both a liquid to a solid phase transition, correct?
Yes. So in alkanes, what I would expect is a greater degree of disorder, which would like across, if we consider the surface of these alkane molecules, then there would be a greater degree of disorder, which I think would make like these temperature transitions at different points, these would be different because they have at different orientations at different degrees of these different degrees of these disorders. We would have different potential energies. But in lipids, since they are
1 second. I think you don't have to now say with the lipids, but is the disorder of the surface that's important for you, or there's something else that's more important?
I mean, by surface, I'm just talking in the sense of a single layer. So if by surface you mean at the something analogous to a lipid head group, then at the surface it won't be that important, but lower down the chain it would be more important.
Oh, so you're looking at single layers, and then that is the surface that you're referring to. You're not referring to the surface of a melt or a big bulky liquid in a solidifying container or something.
Not exactly in my explanation.
Okay. All right. So yeah, I'm done with my questions. Thank you.
Does anyone else have any questions for them?
Anubhav, should I go ahead with asking them?
Sure.
Okay. So in your question, the fuel crisis question, you said that you have not used any confirmatory test. Can you please explain the logic for not using a confirmatory test?
Well, I mean, not exactly a confirmatory test of T10 plus I form. I have used confirmatory test because let's suppose, I think you can see my pointer. In this case, there are only two possibilities. We have either the molecule, either the element A or nothing. So if we have some form of some test which can at least tell us whether A is surely present or not, then that would be enough. We don't need a confirmatory test per se, like a T10 plus I form. So T7 would tell us that A is present or whether A is absent. That's what it says.
Okay. So this is with reference to the qualitative analysis that you have probably done in class 11th and 12th. So even if you have a very good indicator, or you have isolated that a certain element is the like a certain ion usually is the only one present, do you still perform a confirmatory test on it?
Yes, we do.
Yeah, so basically I would like to ask, like, what is the reason that you have to perform a confirmatory test rather than even if you can give a clear-cut answer from the indicatory test?
There, I think in this context there could be some impurity still present after precipitation or separation, anything which might give a false positive.
Yeah, so the main idea behind a confirmatory test is that it gives a clear, unambiguous answer, right?
Right.
So you know that if a test is positive, it must be A. It cannot be anything else, even though you have concluded it. So, won't you think that it is possible that your element which you have finally gotten is not the confirmed answer? Even if you have eliminated everything, is there no motivation behind performing a confirmatory test still?
I mean, if we can assume that the precipitation or separation which is happening in this difference here, like if we assume there is some separation of these elements, then I wouldn't think there would be any point to doing the confirmatory test. But if there isn't any separation as such, then we would need to do a confirmatory test.
Okay, thank you.
Okay, I think, are there any more questions from the judges? If not, we can move on to Team A. Okay, you can unshare your screen, and Team A, you can start sharing your screen. This is the last presentation for this round.
Hello.
Hello. Yes, this is Arpan Basu and Aditya Sakrikar.
So I'll be, explaining the points, and my friend Aditya Sakrikar will be sharing the corresponding page at that time.
Okay, go ahead.
So we'll first discuss the fuel crisis question. So seeing the discussions of the earlier teams, I feel it is pertinent to state clearly the assumptions that I have made, that we have made. The first assumption that we have made is that all 10 elements are already segregated but unlabeled. So we have to label them. The second assumption is that even though we logically know that after some elimination process, as Sherlock Holmes says that if all possibilities are removed, then what remains must be the only thing, right? But in chemistry, we still need to perform a confirmatory test. So that's why even after logically deducing that some element must be the only one that remains, we still perform the confirmatory test. So to aid our process, we made this Excel sheet, and actually we derived great benefit from it. So let me explicitly explain to you our algorithm. Can you move to the next page, please? Yeah. So first of all, we conduct the test T1 on all the elements. So that will cost us 50. So if you see the characteristics for T1, there can be only two possible yeses, two possible no's, A and B. Okay, so that's a minor typo. There can be only two possible no's, and T1 gives no indeterminate results. So we can isolate the two no's, A and B, and then we can perform the CT, confirmatory test, for A. So we'll be able to distinguish A and B by that way. So technically speaking, logically, we only require that one confirmatory test to distinguish A and B. But as Aryaman mentioned in the previous presentation, we still performed both the confirmatory tests to be 100% sure that we have got A and B. So we got 20 for the CTs. So here it is written.
Come in here. So it's 30 because if we perform the CT of A and if the first element is B, then it will give a false. It will give a no. So we will have to perform it on the second element, which gives a yes. So that costs 20. And just to be sure, again, we perform the CT of B on the remaining element, which we already know is B. But just to confirm, we will perform that. So that gives us 30.
Okay. So logically speaking, so like in an algorithmic terms, we have performed more CTs than required, but as we are mentioning again and again, we have to confirm fully that the elements we have isolated are indeed the ones. So then we can you just scroll down, please? So then we conduct T9 on the 8 remaining. Now there are two possible things that can happen here, and these two possibilities are caused due to the indeterminate results, right? So if you see the table for T9, you will see that there is one indeterminate result in T9. See for B there is an indeterminate result for H. Yeah, for H there is an indeterminate result, right? So if that indeterminate result, so here we have made another assumption that an indeterminate result is like a random variable. It can either be yes or be no. To take care of both the possibilities. So in the first possibility, if it comes out to be yes, then you just separate out the no's, which you know to be E and G. Then you again conduct the CTs 30, that costs 30, and now you have identified A, B, E and G. For reasons that will become clear soon, we will then also confirm. We will then perform the CT for H, all the remaining elements. That will cost us 60, and then so we have finally identified A, B, E, G and H. Now there was the other possibility that the indeterminate result gave us no. So then we have obtained E, G and H. Now then again we have to perform a series of CTs to ascertain. They cost a total of 60. So now we have A, B, E, G and H again. So you now realize why we performed the H CTs earlier. So to bring both the possibilities to the same level, A, B, E, G and H. Now if we conduct T2 on all the remaining, so now it is a similar procedure. I will not explain that again. You will see that in a cost of around 130, we can identify all 5 elements, correct? So we went a step further and actually calculated the cost. So as we said in that T9 test, we had two possibilities. So corresponding to the two possibilities, we have two possible costs. So the worst case scenario, we still have to spend only 35.6 whatever units per element. This is our cost, right? Okay, so this is our fuel crisis question. So now we come. So will the fuel crisis questions be asked now or at the end?
All questions will be asked to you at the end.
Okay, so now we move towards the baby warmer. So as again, we did our research for baby warmers, and so for that we found out that you need phase change materials. So the most common phase change, and that too a phase change material which melts around 36 degrees. So the first such possibility which Wikipedia throws up, we have given the link here, is a paraffin 20, a 20 carbon alkane. But as it was clearly mentioned that paraffins are not suitable for this purpose, so we rejected it. Then we moved on to other organic possibilities. There were quite a few inorganic possibilities too. So the other organic possibilities we obtained uric acid and something called ATP36. So there is a company which commercially sells these PCMs. We have given the links for both of them here. You can check it out. Can you go to the next page, please? Can you scroll down a little bit further? Yeah. So there we have basically used two materials, capric acid and ATP36. So now designing something involves many aspects. So we have actually given a model for how our this baby warmer would actually work. So we would have like a bilayer kind of structure, kind of like the pouches we have, except that it will be shaped like a blanket to keep the baby warm. And the bilayers, the outer layer will be heat insulating. So, heat is not taken away from the baby, while the inner layer, which is in contact with the baby's skin, will be conducting so that, thermal equilibrium can be achieved. We also predicted that there will be a kind of hysteresis, as the professor was mentioning some time ago. We incorporated measures for reducing that within the design itself. So you see near the outer layer there is a kind of jagged thing. So let me explain what exactly happens. So the first time around there is a liquid, suppose temperature drops, it freezes. Then the temperature rises again and it melts again. But you see, when it melts again, the melting process will not be perfect. 99% of the solid will melt again, but 1% will be, spread as very fine particles in the liquid, kind of forming a colloid. So over time, you see the concentration of the solid particles will increase in the liquid, and after a long period of time, these the liquid will kind of become like a slurry. So in hysteresis language, we call it the fatigue of this. And a visualization of this method is also a possible way of checking it out in the lab. So we can artificially simulate the hysteresis of this fluid in the lab. Like we heat it up and then cool it down every 10 minutes and see how long it takes for this liquid to become a slurry. And based on those lab results, we can find out methods for prolonging this liquid's shelf life basically. And as for the jagged thing, this jagged thing is basically rough, so it will basically encourage those solid particles to settle there. So this is a design feature which will enhance the liquid's shelf life. 2.5 minutes left. Please speed up. We have also performed some calculations. So the temperature, as we said, melting temperature should be around 36.5 degrees centigrade. The weight of a baby is assumed to be 2.5 kg. The specific heat of the human body was taken to be 3.6 kilojoule per kilogram. And suppose the temperature varies to be dt. We will determine dt later. Please scroll down. So based on that, please scroll down. So based on that, we have calculated, the amount of capric acid. So approximately 110 grams of capric acid and 75 grams of ATP36 will be needed in that pouch. So, so this is, some preliminary calculations and design thought out. And there are, of course, in any design problem, there are many aspects. Some which we try to predict from beginning was that, when these melting and freezing occurs, there can be significant volume changes. So, there must not be, so we should, try to pick materials in which this volume change is minimized. Obviously, another important point is that we should not take things which have biohazards associated with it, because first of all, such things are unsafe near human beings, and here we are talking about anyways sick baby. So our chemicals, any material we use has to be very secure and safe. So yeah, these are the two problems we solved and our rationale behind that. Thank you.
Okay, the floor is open for questions from the judges.
Okay, I can ask some more questions on this warmer problem. Thanks for doing this. Can I ask you a question about, are you comfortable with homogeneous versus heterogeneous nucleation?
I have heard of the process nucleation, but I cannot. So yeah, go on. I'll see how much I can answer.
Let's test your depth. Yeah. So tell me, what is the origin of hysteresis in these first order equations?
So here, so for that we will have to understand the process of freezing. So how does freezing happen? Freezing happens when there is some nucleus in the liquid around which initially a preliminary amount of liquid freezes to form a solid, and so that forms a bigger nucleus, and once there is an enough concentration of nuclei in the fluid, the freezing happens rapidly. This is also the reason for supercooled liquid. So if purify some liquid too much, keep water at -10 degrees centigrade at atmospheric pressure itself, supercooled water, but the moment you disturb it, it will freeze. So that is the basic concept of nucleation. So hysteresis in this context will arise because as I said, there will be small nuclei of solid PCM that will be left around, and when the liquid tries to freeze again, it will have a relatively easier time doing so, because it already has a certain threshold of nuclei available upon which it can condense. So yeah, so that will be the cause of hysteresis. Every time the freezing process becomes slightly easier than in the earlier cycle.
Let's just make a critical situation. I added certain, let us say, particles of I don't know, some impurity. I just added some nanoparticles of an impurity, right? Which facilitate, and I will say they are not hydrophobic. Okay, they are hydrophilic. And let us assume that we are considering only the solidification of water here. And in this scenario, what will happen to the hysteresis versus a pure phase of water?
It actually depends on the concentration of the impurity you have added. So we have also read of the ebullioscopic and the cryoscopic constant. So if you add too much, then the melt will change. But suppose if the concentration of impurity added is not that much, so that this Kf and Kb come into picture, then the freezing process will become slightly easier, because then it will have some nuclei.
Okay, yeah, so I'm essentially in a regime where we are not worried about chemical interactions, okay? And then these are, just assume it's like a stone that you dropped into water or something, where you neglect any chemical interactions. So in that case, would you expect the hysteresis to go down or go up?
Freezing will become, the freezing would be facilitated.
Okay, so what will happen to the hysteresis?
If you repeatedly, melt and freeze, melt and freeze, melt and freeze. So yeah, the hysteresis, the material, the water will reach fatigue faster.
Okay, what does that mean? The question is, would the hysteresis go down or increase?
So like I have not read the exact textbook, you know. So I think it would.
Hysteresis is the difference
fatigue
between.
Faster, yeah. So.
Okay, that's fine. So now, do you know if what are the compositions of this ATP or whatever that you came up with? Did you try to look for the composition?
In the 2 hours, it was not enough time to actually read what was inside the ATP.
Okay, that's fine. And any information about the range of freezing of these materials?
So all of these are 36.5 degrees. As we said, we have assumed DT to be 2 degrees. So I think if it is pure enough, then it will have a sharp freezing point.
Okay. Do you understand the term eutectics?
I have.
That's okay. If you don't,
I cannot
answer. No. So one last question for you. Now you considered that most of the heat is being dissipated by the baby here, correct?
Dissipated or absorbed depends on whether hypothermia or hyperthermia.
That's fine. Yeah, I mean, and now do you think it's mostly the baby that's going to lead to essentially the losses of the heats, or essentially let us say heat being either absorbed or phase change material? Is this predominantly the baby or is it predominantly the surroundings? In your case, you
I think in the scenario described in the question, it is predominantly the baby will be the heat sink, because the question has been framed in the context of the baby suffering hypothermia and consequently dying. So yeah.
Okay, but baby could be suffering from hypothermia because it's unable to keep up with the external heat exchange, but maybe it still has certain, I mean, you still have like metabolic processes happening inside the baby, correct?
Mm-hmm.
They'll still release some heat, correct?
Mm-hmm.
But maybe they might not be able to keep up with the external surroundings, the heat exchange with the external surroundings.
So you see that the latent heat of fusion of both these fluids, for capric acid, I think it is 163 kilojoule per kilogram, and for ATP 36, it is, I think, 240 kilojoule per kilogram. So these are, quite large values. So you are describing that cope up with sudden temperature changes, that is unlikely to happen because these liquids possess a certain amount of inertia with respect to sudden temperature changes. So I think that should be a large.
My question is, Arpan, sorry, my question is, why did you ignore the heat exchange with the surroundings? That's the question.
Oh, that was because of my design. So can you just go to the previous page, please? So you see, we have specifically designed the outer layer of the blanket to be a heat insulator. So, we have kind of like eliminated that possibility from design of that baby warmer.
Okay, thank you. Yeah.
If someone has questions relating to the other question, please ask them a little fast. We have under 2 minutes left for this round.
Hi. So I guess by now you know that was not what we were going for, but that is fine. The order of the test shouldn't change anyway. It's positive and negative. So, yeah.
I did not get you.
Okay, right. So, well, the thing is, the question was not that you have 10 test tubes in front of you and you have to label them. The question was that if you are given a sample, you have to identify which element it is.
Yeah, that's what I said. I did not say labeled. I said unlabeled. 10 elements which are separate from each other but unlabeled. So we do not know which is which. So we have to identify them. So yeah, I did not assume labeled test tubes.
Yeah, not labeled. I get it. But see, so the thing is, it's not that there are 10 test tubes, right? So think of it like the qualitative analysis you do in the chemistry lab. Given one test tube with one element, and you're supposed to identify which it is. So, right, anyway, what you're minimizing there shouldn't be an issue, right? And you have got all the confirmatory tests in. But So like I said, the cost is going to change a bit. So because the test one which you have done, you're saying that you will do the test one 10 times. Okay. Now,
Yeah,
let
we'll
us
identify 10 different things.
so wait, so now let's say that you have 10 test tubes in front of you, right? 10 unlabeled test tubes.
Mm-hmm.
Do you really need to do it 10 times?
No, as we said, we did not perform it 10 times. That's what our algorithm kind of cut short. That would be the most, perform 10 cities, but that is not our aim. Our aim is to reduce the cost as much as possible, and cities are the costliest. So yeah, we did not perform the cities 10 times.
No, not the cities. The test one which you did on all the 10 test tubes, right? In the start, if you can scroll down a bit. Right. So you said conduct T1 on all, right? If you have 10 test tubes, do you need to conduct T1 on all of them?
In the specific procedure that we have described, yes. I could think of an alternate one where you do not have to perform, but yeah, in the procedure we have described, we conducted T1 on all of them.
Right. So yeah. So
I would just clarify one thing. So for T1 we have only 2, if I'm not wrong, no's. So we have taken kind of the worst case scenario. So if all the first 8 are yes, then we will have to, for identifying the 2 no's, we will have to perform the T1 10 times. And for the further test, the ones we have identified have been removed from the set of the 10 test tubes.
Yeah, so as you said, the best case possibility that, we conduct T1 on 2 test tubes and they happen to be A and B. So the best case is 2 tests. Yeah, but in the worst case, where, the first 8 all turned out to be yeses, then...
If the first 8 all turned out to be yes, do you need to do the test on the last?
Logically, no, but from a practical viewpoint, yes.
See, because the confirmatory test you're doing again anyway. But anyway, fine.
Okay. I get your point. We could have. We could have cut some slack there.
Right. Okay. Thank you.
Thank you, everyone, for all your presentations. This was the last presentation of the subjective round. Following this, we shall part for lunch, and we shall be back at. So we went about 15 minutes late. So let's be back at 3:50. I guess that should be okay, right?
Yeah, 3:50 is fine.
Okay. Then let us meet at 3:50, and in case the judges want to discuss about this round, we can meet in the judges channel.
Yeah, let's do that.
Okay. Let us reconvene at 3:50 for the final round, the analysis design round. Thank you.